Hi, I'm Dr. Papia Bhattacharjee. In this problem, we are given this function. It's the series, power series, x over 3 to the power n. And we have to find the radius of convergence of this function. And then we have to actually find the radius of convergence of the derivative of the function, the second derivative, and the integral of this function. Okay. So in this first video, we just compute the radius of convergence of f. And in the next ones, we'll compute the other radii of convergence. So notice that this function is written in a compact form, x over 3 to the n. It's probably not a bad idea to rewrite the expression a little bit, and you will see later why it'll be helpful. So I want to rewrite it in such a way that I can extract the x component out, okay, and then write it in the general form of a power series. So I can see the center of the series nicely. So what do I mean by that? All I mean is separating it into x to the n divided by 3 to the n. Look, as soon as you write it this way, this looks like an an x minus c to the n, the general power series form. And you see right away that the center of this series is 0. Okay? That will be helpful because you are computing the radius of convergence. All right. Now, recall that we use ratio test to find the radius and the interval of convergence. So we'll do the same here. Okay. So let's apply ratio test. And to do that, we have to write down the nth term, which is right here, x to the n over 3 to the n. And then from there, we have to write down the n plus 1th term, a n plus 1, which is nothing but rewriting or changing n to n plus 1. So this will be x to the power n plus 1 over 3 to the power n plus 1. And now for ratio test, we form the ratio and take the limit. So let's take the limit as n approaches to infinity. Remember, there's absolute value of the ratio an plus 1 over an. Okay, so now an plus 1 is in the numerator, so that fraction you keep it as it is. So this is x to the n plus 1 over 3 to the n plus 1. And then an is in the denominator, so that fraction will be flipped and multiplied. So it will be 3 to the n over x to the n. Okay. Now, look at the like terms. See the x to the n plus 1 and x to the n. They will cancel, and there's an extra x in the numerator, so we'll have an x. And then the 3's, they will cancel as well, and there's an extra 3 in the denominator, so we'll have a 3, and then absolute value. Don't forget the absolute value, it's important. Okay. Now, look at that expression. It's absolute x over 3. So there is no n. What does that mean? N is the variable, right? N is approaching to infinity. And absolute x over 3 is just a constant. So what is the limit of a constant? It's just constant. So the limit is absolute x over 3. Let's just rewrite it one more time. See, 3 is already positive, so we don't need absolute value next to it, right? But x can be negative. So this is the same as absolute x divided by 3. The reason I wrote it this way is because it will be easier to figure out the interval of convergence. Now remember, this is ratio test. What does ratio test tells us? That if the limit is less than 1, then the series converges. So less than 1 implies converges. So let's see what that means. What does it mean by absolute x over 3 less than 1? That means multiply by 3 both sides. So absolute x is less than 3. And what does that mean? You know how to solve inequality involving absolute value? you take out the absolute value, and x will lie between negative of this number, negative of 3 and positive 3. Okay, so this is our interval of convergence. And therefore, let's figure out what the radius is going to be. So, in the number line, the center of this function is 0. So, 0 is the center, right? And the interval is between negative 3 and positive 3. So, what is the radius? It's the half the length of this interval, which is 3 units. So, radius is 3. So, let's come back here and write it down that the radius of convergence of function f is equal to 3. Now, in the next video, we will first compute the derivative of this function and then find its radius of convergence.